So now that we know what a linear transformation is, what are some of the things that we would need to learn about a linear transformation so that we get to know its algebraic properties? And the first real good example of the things that we would want to know about a linear transformation are its image and its kernel. So let's have a short sort of exploration about what the image and the kernel of a linear transformation ought to mean. So if we think about linear transformations from the point of view that we sort of started out with today, where it's a function from a domain to a codomain that also satisfies the respecting linearity properties, right? That the transformation of a sum is the same as the sum of the transformations, and that the transformation of a scalar multiple is the same as the scalar multiple of the transformations, then one of the ways we can think about image and one of the ways we can think about kernel might be something like this. If I have a linear transformation like let's say this one that I'm looking at here, where it looks as though what I get when I transform this cat face is just kind of a rotated and maybe slightly larger version of the same cat face in the codomain, then the image of this linear transformation is going to refer to every green vector that it is possible for me to obtain in the codomain as the image of one of my purple vectors in the domain. So all the green vectors taken together collectively form the image of my linear transformation. And so speaking in notation, as mathematicians so often like to do, the image of a linear transformation is the set of all elements of the codomain which can be obtained by applying f to an element of the domain. So it's all the w's in the codomain space w, such that w is equal to f of some v from my domain. So for this particular linear transformation that we're looking at with the cat face, that image looks like it is the entirety of the xy plane, because there's no green vector that I can't get as the image of some purple vector. And we can contrast that with what we might get with, say, this linear transformation, where it looks like the green vectors that I can get are all sort of constrained. They're constrained to just a line. It looks like that line is the line that has the equation y equals 2x in the codomain plane over here on the right. And so clearly different linear transformations can have very different answers for what are their images. But sort of the nicest case, the cases that we're probably most interested in general, are the cases where the image ends up being the entirety of the codomain. And in such a case, we would say that this function is an onto function. Remember the word onto from when you studied functions for the first time. An onto function is one where all of the possible outputs that could be obtained out of the function actually are obtained as outputs for some input of the function. So when I have a function into R2 and its images span all of R2, then we would call that an onto linear transformation. Sometimes also use the word surjective for that kind of linear transformation. We might also use really fancy words like epimorphism for that kind of transformation. We probably won't use a word quite that fancy. We'll probably just stick to the word surjective. So a surjective is a linear transformation whose image is the entirety of the codomain. So that's the image piece of the pie. The other piece is the kernel. I'm going to put the cat nose back at the origin one more time here. So linear transformations, as we talked about in our introduction, always take the zero vector from the domain and send it to the zero vector in the codomain. So the cat nose at the origin ends up having a cat nose at the origin over here on this side as well. But it might be the case that there are other vectors that are also getting sent to the origin as well, besides the zero vector. So let's see if we can make such an example here. So I just need to get that green vector to be the origin without having the purple vector be the zero vector. Here's an example. Right. So this purple vector v, its image is the zero vector in the codomain. And so this is an example of a linear transformation that actually has a bunch of different domain vectors v that all have the property that their codomain vector, their image vector, is the zero vector. And so the set of everything which gets sent to the zero vector is what we call the kernel of a linear transformation. So the kernel of a linear transformation is the set of all vectors v in the domain, which the function transforms into the zero vector of the codomain. So it's all of the v's that solve the equation f of v is equal to 0. And so if we put our sort of cat nose example back on here, we can't really see what's going on with the cat's picture because it's being squished down from a two-dimensional square into probably a one-dimensional image that we can't see over on the right-hand side. But we could know, for example, that this portion of its eyeball that my vector v is pointing at here would be getting sent to the 0 vector in the codomain by this particular linear transformation. So that's the definition of image and the definition of kernel. But of course, the question arises, how are we supposed to find either of these things for a given linear transformation? And that's going to require us to do the next piece of work, which is going to be to talk about how to find a standard matrix for linear transformation. But before we get there, we should try to uncover what kind of object is the image of a linear transformation going to be, and what kind of object is the kernel of a linear transformation going to be. Because a priori they just look like sets. Right? It's the set of all outputs that are associated to some input, and it's the set of all inputs which are getting associated to the 0 vector output. Right? But in fact, fortunately for everybody concerned, a little bit more is true about kernels and about images. And the little bit more that's true is that both the image and the kernel of a linear transformation are themselves vector subspaces of the respective domain or codomain, whichever one we happen to be talking about. So you'll notice, for example, that in this example here, where the image seemed like it was a line through the origin, well, a line through the origin in two-dimensional space is an example of a vector subspace of R2. Same thing with the kernel, that all of my vectors that wound up getting sent to the 0 vector, they look like they lied too along a common line through the origin. It looks like the line y equals minus x in this example. Right? All those vectors are getting sent to the 0 vector in the codomain. So both the image and the kernel are vector subspaces of their respective codomain or domain of my linear transformation, respectively. So that means that if the question asks us to do something like find the image, or find the image of this linear transformation, or find the kernel, what we often are doing is we're finding a basis for it. We're describing those subspaces by finding a basis for them. So let's start with this activity, 3.3.4. And in this activity, the question is, here's a linear transformation. So we're going to sort of take on faith for the moment that this is in fact a linear transformation. It sends a 4-dimensional vector x, y, z, w into the 3-dimensional vector given by these components. And so the question is, how do I find a basis for the kernel of this linear transformation? Well, before I turn you loose on this example, let's just remember what it is that kernel actually means, and then that will help us to sort of get off to the races on this problem. So this is activity 3.3.4. Then to do this task, what I'm actually trying to do, remembering that the kernel is by definition the solutions of the equation f of v is equal to 0. Really all that we're asking to do, if we're trying to find a basis for the kernel of t, this is exactly the same question as solve the equation t of v is equal to 0 and express your answer as a span of a linearly independent set of vectors. That's all we're doing when we're finding a kernel. We're just solving a homogeneous equation. Right? The kernel is the solution space of the homogeneous equation for the vectors which would result from factoring out my variables here, factoring out my x's, y's, z's, and w's. So let's take 10 minutes or so with your team. It's numbered activity 3.3.4. This is an A3. And I think in the file its number is, let me go get the right number for this one.
I think it's 3.3.6.
3.3.6, thank you. Yes, it is 3.3.6. So let's do 3.3.6 for the next 10 minutes in your breakouts. If we're finding a basis for the kernel of this, what we're really actually doing to find that basis, I'm going to switch back over to my other camera here for just a minute, is that we're solving the equation t of v is equal to 0. And then we're expressing the solution that we get as a span of a linearly independent set of vectors. So all we're doing is solving a vector equation. This is something we learned, the first thing we learned this semester was how to solve a vector equation. And so to do that, this team just sets up the vector equation for this by factoring out the x's, y's, z's, and w's, and then turns that into an augmented matrix equation, which is homogeneous. It has a right-hand side that's the zero vector. Finds the reduced row echelon form, discovers that there is one free variable, which is the second column, the non-pivot column here. So they let y equal any real number a, that's my free parameter. They solve for x, y, and w in terms of a, and it turns out x needs to be minus 2a, and z and w are both 0. And so by factoring out that free parameter, they find a basis for the solution space to be the vector negative 2, 1, 0, 0. So the kernel of this linear transformation is that vector subspace of R4, which is spanned, has a basis of the vector minus 2, 1, 0, 0. So every multiple of minus 2, 1, 0, 0 in four-dimensional space is getting sent to the 0 vector by this linear transformation. And only those elements of four-dimensional space are being sent to the 0 vector by this linear transformation. So that's how we find the kernel of a linear transformation. Finding the image is a little trickier. Because we need a better way. We need a way to do in general what this team did in this one example here, which was to take a expression of a linear transformation as a function and come up with some matrix that represents the action of that linear transformation. In other words, going back to my cat face one more time. Right. I want to find a matrix that completely describes how all of the points in my xy plane are getting transformed from domain into codomain. And so that's our last topic for the day.